Tonight on Nova.
We've now realized, or beginning to realize, that the visible universe is only a fraction of what may be there. What I call the invisible universe may be as important as the part that we can see.
A satellite called IRAS made the invisible visible.
I kind of liken the excitement of the launch to perhaps the moment of Columbus setting forth to look at the New World. We knew that we were opening a new window on the universe and that this was likely to change man's entire outlook in ways that we could only guess at and conjecture about in some respects.
Go behind the scenes of a triumphant adventure in space technology. Countdown to the invisible universe.
Major funding for NOVA is provided by this station and other public television stations nationwide. Additional funding was provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials.
There is news from across the universe. In these strange new images, news of the birth and death of stars, of other solar systems, of turmoil in galaxies far beyond our own. Discovered by a satellite called IRAS that extended our range of seeing into a new world that had always before been invisible to us, the world of the infrared. These infrared images will forever change the way we think about the universe.
We got an altogether new view of what our galaxy looks like at infrared wavelengths. And I mean, it's just an enormous, stupendous new view of our universe, and our universe is absolutely spectacular.
One of the exciting aspects of IRAS is that it was really looking at the sky in a totally new way. We can now study in a very deep way how the universe is put together, where stars come from, where planets come from, what the ultimate fate of the universe really is.
The nighttime sky. When seen with the naked eye, it appears to be composed of pinpoints of light, a multitude of stars in a vast emptiness. But our eyes alone can deceive us. "300 years ago, people believed that everything there was to know of the universe was already understood. Until the scientist Galileo, using the newly invented ground glass telescope, made some unexpected discoveries about other objects contained within the sky. When he turned his telescope to the point of light that was Jupiter, much to his surprise, he found it to look like this, surrounded by moons. For the first time, it was possible to look into the heavens in a new way. With the increased sensitivity of his amplified vision, Galileo was able to perceive something which had until then been invisible. Thanks to a single new tool, the science of astronomy was born. For hundreds of years, astronomers continued to refine the technology of optical telescopes. Every time they looked through a more powerful instrument, they made new discoveries that tested their notions of the cosmos. But despite these advances, the sky still contained mysteries. There was only so much they could learn, no matter how powerful their telescopes. The optical astronomers were able to see these objects because they emitted energy in the form of visible light. But visible light is only one way that information comes to us from the heavens. Throughout the universe, matter emits energy in the form of waves, known as the electromagnetic spectrum. But if that energy doesn't happen to fall within the narrow band that we sense as visible light, then we can't see it. The other energy wavelengths are invisible to us. But invisible or not, space is filled with energy emitted at all wavelengths, and all of it carries important information about something that is happening or has happened somewhere in the cosmos. Yet much of this information remained hidden until astronomers created the tools that could make the invisible visible. Technological advances only possible in this century began to reveal the universe of the electromagnetic spectrum. In the 1940s, the huge receiving dishes of radio astronomy started to collect signals from space that found more surprises. The existence of strange new celestial features, such as quasars and pulsars. X-ray astronomy was not far behind, yielding even more secrets from the invisible spectrum. With each technological breakthrough and the unexpected information they found, scientists were able to build up a picture of the universe far richer than Galileo could have dreamed. Yet long after the sky had been thoroughly surveyed at visible and radio wavelengths, and even after ultraviolet, microwave, X-ray, and gamma-ray surveys had been made, the picture was still not complete. A 200-year-old puzzle remained in the infrared portion of the spectrum, the energy we feel as ordinary heat. In 1800, in a classic experiment, astronomer Sir William Herschel used a prism to break up the sun's white light into the rainbow colors of the visible spectrum. Using crude thermometers, he found that each color was a different temperature. And even when he could see no color, Herschel measured an increase in temperature. The first to discover an invisible portion of the electromagnetic spectrum, Herschel named it infrared. If our eyes were sensitive to infrared, we might see a matchstick man this way, with different shadings that reflect different levels of heat intensity. The point of greatest heat, the head of the burning match. Everything in the universe, every dust mote warmed only a few degrees above absolute zero by distant starlight. Every planet, star, and even the universe itself emits some heat or infrared radiation. The information contained by this invisible infrared universe was a crucial link in the quest to understand the cosmos. But astronomers had no way to explore the vast infrared universe and reveal its secrets. For the mysteries of infrared, although tantalizing, represented a special challenge for astronomy. The Earth's atmosphere blocks out all but a very few infrared rays, and even those which can get through were poorly recorded because there was no suitable detector to pick them up. Until in the early 1960s, physicist Frank Lowe used the exciting new findings of solid-state technology to invent one. The germanium bolometer or heat meter was the result. The instrument, a supersensitive thermometer, was able to detect the slightest heat radiations. 1,000 times more sensitive than earlier detectors, it was certainly a good start. The next step would be to find a way to apply the heat meter to infrared work.
I was aware that this large gap in astronomy existed, and I thought, well, now we've taken the first step. We've got the detector. What else do we need? And perhaps we can go and do some serious exploratory work.
The detector had solved one of the key problems facing infrared scientists. A NASA jet solved another. It gave Lowe the height needed to get above much of the atmosphere blocking out the infrared. But the detectors can only measure heat if they are colder than the objects being observed, so Lowe had to cool the sensors. He built a thermos containing liquid helium around them, lowering their temperature almost to absolute zero, minus 273 degrees Celsius. This made the detectors exquisitely sensitive to heat radiation. Other scientists had taken a different approach. They worked with balloons, which can fly to 100,000 feet, double the height of Lowe's jet. Both techniques met with some success.
And this indeed did show that the center of our galaxy, many regions of star formation and so forth were extremely bright sources of infrared radiation.
But the trouble with balloons and airplanes was that flight duration was only a few hours at most, and the balloons were difficult to control. And neither technique could completely eliminate interference from Earth's atmosphere. Still, their results were enticing. Very bright sources of infrared had been detected. But the astronomers knew that these findings only hinted at the vast infrared universe. There had to be more waiting to be discovered. The limits on their Earthbound explorations caused the scientists great frustration. After all, this was the space age. Astronomers everywhere were eager to explore the infrared universe more effectively. In Holland, a country with a proud reputation in astronomy, a new idea was born. The year was 1973. Dutch scientists were convinced that a satellite could solve the problems of investigating in the infrared. It was here that the Infrared Astronomical Satellite, IRAS for short, became a real possibility. In the Amsterdam Planetarium, Dutch scientist Dr. Reinder van Dijnen describes the thinking behind the great experiment in infrared which was about to begin.
Building the telescope actually into the satellite and surrounding it by a vessel which contains liquid helium would allow us to do two things at the same time. We would get rid of the residual atmosphere, which always plagues us when we do balloon astronomy. And the second thing we could do is we would really cool the telescope down to very, very low temperatures, which we are unable to do in a balloon telescope.
But in order to achieve this dream, many things would have to happen. Most of them had never been tried before. The technological challenges were staggering. Like Frank Lowe's airborne telescope, IRAS's sensors would have to be kept so cold that they could detect the faintest glow of heat energy from the sky. So liquid helium in a vast thermos would keep IRAS's eye close to absolute zero. But eventually it would evaporate. The mission would last only as long as the liquid helium lasted. Radiation picked up by the telescope would be focused onto 62 infrared detectors, designed to pick up different infrared wavelengths. Each detector would be paired, so that a hit recorded by one could be confirmed by its partner within a second or two. It would be necessary to orbit IRAS clear of the Earth's atmosphere. But the satellite would also have to circle below the Van Allen belts, formed by the Earth's magnetic field trapping particles from the sun. They start around 800 miles above us, and they would swamp the sensitive detectors with false readings. So they decided to orbit IRAS about 540 miles up. There would be 14 orbits a day, each one taking 103 minutes, riding between atmosphere and radiation belts. Each orbit would overlap the previous one. This would allow confirmation of a previous sighting, another way of ruling out false detections. The IRAS project was too big for the Dutch to handle alone, and they approached NASA with the idea of international collaboration. Soon, IRAS had become a joint Dutch and American project. The Dutch were to build the satellite, computer, flight control systems, and power supply. The U.S. team would make the telescope and the enormously tricky cooling and detection system. Launch was set for February 1981, but the problem started right away.
In the case of IRAS, we were taking a tremendous step forward in engineering, in the technology that we were trying to accomplish. And this tension was, I would say, particularly great in this mission.
And we have had real difficulties. An example, the Dutch industry had to start rather too early in the program. The definition of what the American counterpart was going to provide to us was not that clear when we started. And as a result, we had a real difficulty of trying to adjust the interfaces that we both had to meet.
Some of the IRAS problems were normal aspects of international collaboration. Others were due to the extraordinary demands of the scientific mission.
Ordinarily, one would like to have perfect assurance that everything is under control. But in a pioneering mission like IRAS, that's just impossible. There were a lot of things that had never been tried before, and we didn't know for certain that they were going to work.
The satellite moves with great speed around the Earth. It takes about 100 minutes for one complete circle. And while you're doing that, you have to keep pointing that telescope to the stars. And you have to avoid, and this is very important, that it points to the sun or to the Earth. So both cases are dangerous. Because if the sunlight gets into that telescope while it's cooled with liquid helium, one would evaporate the liquid helium almost immediately and the mission would be lost. And the same holds for pointing it to the Earth for any duration of time. So we had to be very careful to design the control system of the satellite such that it doesn't point to the sun and it doesn't point to the Earth.
Ja, naschakel ik de tokker.
Dan schakel ik de klok in.
Ja, eenmaal.
So critical was this flight control system that Dutch researchers built a space simulator at their National Aerospace Laboratory. They represented the sun by the arc light of an old film projector. Here they confirmed the accuracy of the sun sensor and tested the onboard computer and other subsystems. The scientists cleverly reproduced the temperature difference between Earth and space to get the best indication of how the real satellite would work. The Dutch were doing well, but just 18 months before the 1981 launch date, progress in the US came to a sudden halt. Half of the critically important infrared detectors had burned out during testing, and the amplifiers to boost the faint signals back to Earth wouldn't work. One of the problems was that the amplifiers, called JFETs, had to be placed close to the detectors, but at a very different temperature. NASA struggled to cope with the calamity.
The detectors themselves had to operate within 2 degrees of the absolute zero, 2 degrees Kelvin, whereas these JFETs were happiest at about 60 or 70 degrees Kelvin. Still a very, very low temperature because room temperature is 300 Kelvin. So we had to come up with a way of operating the JFETs at the proper temperature in very close proximity to the detectors themselves, which were much colder. We had to keep the infrared radiation from the JFETs away from the detectors completely and introduce no additional heat into this very cold environment. So a number of conflicting problems had to be solved.
At NASA's Jet Propulsion Laboratory, a team of engineers and scientists came together to sort out the JFETs and a mountain of other emerging difficulties. In NASA terms, it was known as a Tiger Team, and one of its teeth was Bill IRAS.
We were under a great deal of pressure because at that time we'd already overspent our budget by a factor of 2. We were a year late in our original launch schedule, and there was a good deal of pressure from all sides to make this thing work. In fact, being on the IRAS project at JPL was, most people would look at you sympathetically as you walked back and forth across the halls because nobody was really sure we could make this work, in fact, including all the people that were working on the job.
Meanwhile, the telescope and satellite body had been joined together in Holland. Then the whole unit was flown back to JPL, where the project's problems were still being tackled in an increasingly frenzied atmosphere. About the only thing cool was the telescope itself, kept secure in its thermos jacket month after month while the scientists labored on. Finally, the Tiger team had a breakthrough. They suspended the JFETs on Dacron fibers and placed them inside a gold-plated light-tight box. The detectors and amplifiers could now happily coexist in the focal plane. The focal plane itself, where an image would be in an optical telescope, was installed into the satellite, but their troubles weren't over yet.
The focal plane was installed, all of the peripheral equipment was installed, and we had the big turning on party where we turn the telescope on and look at the output of the data from the focal plane. We'd all hoped that we had solved our problems and we were home free. The fact is that the data from the focal plane was totally useless. All of the sensitivity that we expected to get out of the focal plane was swamped by enormous amounts of noise coming from we didn't know where. An eighth of the focal plane didn't work at all, and we didn't know why. So that really began phase 2 of the IRAS rebuild process, which was to understand what it is we had created and fix the problems again.
By now, 9 years had passed, and the original launch date had come and gone. There were serious doubts that the mission would ever happen. Yet the IRAS team continued their attempts to put the project back together. A committee of independent experts reviews each satellite program before launch. Unprecedentedly, the IRAS committee was undecided. 2 members were against launch, and the project scientists all had their private worries.
Well, I was one of the most notorious pessimists. I was aware of a half a dozen areas in which IRAS was on thin ice.
One of the difficulties, of course, is that the telescope itself had essentially no moving parts. There was no way to adjust the focus. If it was out of focus when we saw the first star, it would be out of focus for the entire mission. It was also true for many, many other systems. There was no way to adjust anything once it had been launched.
Another big question was, would the cover that went over the telescope and protected it all during the ground testing and the launch, would the cover actually come off? During one of the early ground tests, the cover didn't come off very well, and they had to do a whole redesign. Would it now work? The calculations said yes, but there's no substitute for actually going up and pressing the button.
And there comes a time when you just have to go with what you've got and accept the test results that you have and proceed with the mission.
The launch committee finally agreed and set the date, January 25th, 1983.
There was a feeling that we had been working for years, and now the testing and the building and the training were finally over. You really had the feeling that forces had come together that were necessary to get this thing done. Anticipation was really running high as the countdown ticked away those last few seconds. Night had fallen, everybody was quiet, and then suddenly this tremendous flash. And the spectacle of IRAS leaving the Earth, rising up into the sky on a pillar of flame and thunder. It was really amazing.
It had taken over a decade, but IRAS was finally aloft. The first command to open a valve worked. A faulty sensor was overridden too. The problems on the ground were forgotten. IRAS was alive and well.
Once the cover, this large cryogenically cooled vacuum cover, was successfully ejected into space, never to be seen again, then one's confidence could really rise. And of course, then we saw the first view of the sky. We knew that the detectors were working, the JFETs were working, the pointing system was working beautifully. All of the things that are necessary to make a successful mission started to fall into place.
One of the things that I was tremendously worried about when we were doing IRAS is that it would be a technical success and we wouldn't find anything. And that would have been awful.
IRAS was like our first infrared night. When that cover came off and when we got our first look at the sky with a cold telescope outside the Earth's atmosphere, we finally saw what the universe looked like at infrared radiations. We finally saw what our solar system looked like at these wavelengths.
At last, the skies were open to infrared scientists. The controllers spoke to their satellite via a ground station set up by the third IRAS partner, England, at the Rutherford Appleton Laboratory in Chilton, Oxfordshire. IRAS passed over Chilton twice a day. The ground team had at most only 15 minutes to unload the gleanings of the previous 12 hours, 700 million bits of information. Then they beamed up commands for the next 12 hours, around 1,000 orders for IRAS to obey on each orbit. Each sweep covered a prescribed slice of the sky. The ground operations team of 120 people would monitor the satellite 24 hours a day as long as the mission lasted. The resident astronomer appointed to run the scientific side of the mission, Dr. Peter Clegg, Queen Mary College, London, was among the first to see the IRAS signals.
They were remarkable. They were extremely good, extremely strong, and indeed very much like some of the simulated signals we'd injected. In fact, some of us were a bit concerned that perhaps we were still looking at simulation data and not the real stuff from the sky.
JPL UKOCC voice check. We read you 5x also. We'd like to send you a tape. Can we have your off-ready test online, please?
A space link to Jet Propulsion Laboratories in Pasadena relayed a rich stream of data that was almost overwhelming. Preparing for it and then cataloging it was the job of Dr. Tom Chester.
There's been no astronomical project in the past that ever attempted to cope with this amount of data. As a way of comparison, the sky that you can see with your own eyes contains about 5,000 sources. And that typically is what you see the first time you look in a new way of looking at the universe. You see about that many sources. For example, the X-ray surveys found a catalog of 100 sources. The radio surveys found catalogs of thousands of sources. So it's not too much different from what you see if you do a survey with your own eye. But we, on the other hand, we're dealing with hundreds of thousands of sources. It's a factor of 50 more than what your eye can see, and a factor of 50 more than the usual survey. So we had all sorts of attendant difficulties with data size. We had to have a lot of data storage. We had to have a computer program that could deal with all of the different complexities that are in the data.
This is the raw data, volume on volume of figures which add up to what IRAS saw in the universe. Making something of it wasn't at first an exact science.
The bedlam breaks out almost immediately. When we got the first data in, we were always running willy-nilly trying to process that first data, because it turned out that it came to us in a different form than we expected at the very beginning. So we had to adapt the very first program that we didn't think we were going to have to at the beginning, just in order to read that data. That felt like being at the bottom of a waterfall, just being inundated with water all the time. Occasionally your head would poke out of the water. You'd see a drop of water coming by that you'd understand as a drop of water. But most of the time it was like looking up and not really being able to cope with the volume of information that's coming down.
Dealing with the sheer quantity of information, the equivalent of an encyclopedia's worth of facts every day, was a monumental achievement in itself. In one form, it became a 19.5-inch catalog, the Infrared Book of Genesis.
This catalog is certainly one of the premier achievements of astronomy, because we have more objects in this catalog observed with precise positions and with 4 different infrared colors, which represents a much bigger achievement than almost any other catalog. It increases the number of sources that astronomers have to play with good positions and with good colors, by about 50%. So we've multiplied by 1.5 the number of sources that astronomers have to play with.
Interpreting the raw data, making the invisible visible, was the next order of business. This was done by a technique known as image processing. Each wavelength IRAS scanned was assigned a color, and each infrared source was programmed into a computer. By this method, numbers were transformed into the views we might be able to see if our eyes were infrared sensitive.
One of the most important products of the IRAS mission is an actual picture of the sky in the 4 wavelength bands of IRAS. The spectacular IRAS images are the results of taking the electronic signals in the 4 different wavelength bands and combining them into images that the brain and the eye can work with. We've taken radiation that's invisible to the human eye and color-coded it in such a way that the eye can actually look at it and understand the physical processes going on in a given region of sky.
The resulting pictures are essential for the scientists in expanding their understanding of the cosmos. For the first time, they can map and explore the invisible infrared world. Armed with both the IRAS catalog and the bank of computerized images, astronomers can now attack unsolved problems of the universe with new power and insight.
They can stretch the colors to bring out very low contrast details. They can make the images very high contrast, and they can do numerical work on the pictures. They can ask the computer to give the position and brightness of a star or a nebula that they see on the screen, and the computer will print out numbers corresponding to that. Those numbers can then be compared to theories and used to derive the mass, the brightness, the power output of a given star or galaxy or star formation region.
Months before the work of compilation and computing was finished, the IRAS satellite began to make its scientific contribution. In the very early stages of the mission, 2 American astronomers first spotted something very odd in the raw data coming back from the transmissions. To check the accuracy of IRAS's detectors, the scientists had lined the satellite up on some of the familiar stars in the sky. One of these, Vega, in the constellation Lyra, had no special claim to distinction. They chose it for their calibrations because it's bright, easily seen with the naked eye, only 26 light-years away, and they thought well understood. Yet IRAS discovered something quite extraordinary about Vega. In the centuries before IRAS, astronomers have tried and failed to detect any other solar system in the universe. We've known of only one planetary system, our own, the 9 planets that revolve around the Sun.
And the first time we looked at Vega, we saw that there was something very strange going on with the star. We could compare it with some of the other stars we had been looking at as standard stars, and we could see that it was just much too bright at the longer wavelengths, much brighter than we would have expected it to be.
Vega was emitting more energy at the long infrared wavelengths than was characteristic of a normal star. Its infrared signature was unusual, perplexing, and difficult to decipher. At first, the team doubted their results.
We had not been observing with the IRAS satellite for very long, and we really didn't understand whether it was a flaky instrument, whether it was very a stable instrument. We just didn't know what to think of this observation.
But the readings came out the same every time the satellite surveyed Vega.
It was clear that there was something going on with that star that we didn't understand.
After months of measurement and analysis, the team decided they must be seeing radiation from solid material, dust grains orbiting Vega. Space is full of tiny particles of dust, but the emission suggested that these were larger grains, about the size of pebbles, that had been put into place around Vega while it was being formed, the same process that led to our own solar system. They had found the first evidence for another planetary system in its first stages of growth.
This was something that we hadn't been looking for at all, but by eliminating all the possibilities, we concluded that we were looking at the same process going on around another star. And that just kind of knocked us off our chairs.
Recently, there is more evidence of planetary systems forming around other stars. This is Beta Pictoris, a star in southern skies, in an optical telescope follow-up of an IRAS finding.
The Beta Pictoris example is a very good one. It's very astounding that there's this large disk around that. It's very large in the optical. It's most amazing that somebody hasn't seen something like that, but of course nobody ever thought which objects to look at to try to image to find such things. So we have a long list of interesting and peculiar sources that people will be following up for decades, probably to come.
Although the follow-up studies with optical and radio telescopes are only just beginning to get underway, Vega's irregular infrared signature is now accepted as the first clue to the existence of other planetary systems being born. To date, 12 have been found. The whole process of birth in space, especially of stars, is one area where IRAS material was rich and informative. This is because stars form out of what astronomers call cold matter, invisible to human eyes, but not to the eye of IRAS.
Where are stars forming? Why? What sort of numbers do they form in? Do we get, for instance, low mass and high mass stars forming in the same sort of regions? These are the questions that in star formation we need to know the answers to, and for the first time we're going to get those answers.
The whole question of where stars come from is a topic that really belongs to the infrared. In the beginning phases, a star forms out of the interstellar matter that floats between the stars, these clouds of gas and dust, and these clouds collapse and contract. A star is formed still inside the gas and dust, and it glows brightly in the infrared, but nothing is obvious to either the naked eye or even the most powerful optical telescopes.
This is a dense cloud in space, Barnard 5. Astronomers have long believed that new stars, called protostars, are being born here. As with Vega, IRAS has given us another first, a view of the birth of a star, like our sun.
It's been known for a long time that our galaxy contains clouds of very dense cold matter. We've known about these since the days of optical astronomy because they block out all the optical light. Now, back in 1926, James Jeans predicted that under sufficiently cold, dense conditions, a mass of matter would collapse under its own gravity, and that collapse would continue as the mass became more dense, so that it's a sort of self-perpetuating process. And this process will continue, the fragmentation and the contraction, until it gets to the stage where the matter is so dense that the heat generated by the collapse can no longer escape. And we then no longer have this coldness condition that's required. The collapse will cease to continue, and at that stage we have what we call a protostar.
The analogy you could use is you've got a furnace with a bright flame going on the inside. There's a bright star in there, but the walls of the furnace prevent you from seeing it optically. Yet if you look with an infrared sensor, you can see and feel the warm walls of that furnace. So there's a star in the center that you can see only in the infrared. As stars come to the end of their lives, they start really burning in a very sooty sort of manner. There's lots of solid particles of dust start forming around the star. The star can actually disappear from sight visually, yet be still a very bright infrared source. Then eventually a star, depending on its brightness, may explode in a spectacular way that, again, optical and radio astronomers can study as well. But the IRAS catalog is full of objects that are stars surrounded by gas and dust and that are almost invisible, or certainly not prominent, to optical astronomers. So we can study this whole phase of the cycle of the birth, life, and death of stars using the infrared.
The study of the life cycle of stars could be essential in deciphering another of astronomy's ongoing puzzles, the question of missing mass. At the moment, there isn't enough detected material in space to add up to what physicists think it should contain.
The thing that's so terribly exciting about astronomy today is that we've now realized, or beginning to realize, that the visible universe is only a fraction of what may be there. What I call the invisible universe may be as important as the part that we can see. The so-called hidden matter or invisible universe may be in the form of very cold matter, much of it very nearby the Earth, just outside the solar system, as it were, in the form of brown dwarfs.
Brown dwarf is a star. It's a failed star. It's something like Jupiter, one of our planets, only a little bit larger, that just didn't get to be big enough when it was formed to ignite nuclear fuel. So it's not burning like the normal stars. But one of the interesting questions in astronomy is this question of missing mass. We're always finding at all different scales in astronomy that there's much more mass around different objects than we can see. And you can lock up a lot of mass in brown dwarfs without seeing them because they're very, very faint. They don't have the nuclear fuel, therefore they're not emitting a lot of light. But one of the things that IRAS can do very well is see things that are emitting very feebly in optical light if they happen to be fairly strong infrared emitters. And that's what a brown dwarf would do. It would emit almost all of its radiation in the infrared. So we would expect to find objects that we can see that cannot be seen on optical photographs. There are the interesting cases in which we take a chart, we plunk it down, and we don't see anything. It's what we call a blank field. That has the potential of being any one of a number of interesting objects. We're hoping it may be a brown dwarf or so, but what we have to do is then follow it up, go to the telescope, observe at that position with a more sensitive detector, and see what we can see there. And that will enable us to categorize what kind of an object it might be.
The search is somewhat like the proverbial needle in a haystack, in that the catalog is 246,000 objects. Only a handful of those could conceivably be brown dwarfs. But that search is underway, both here and in California, and I think in other places as well. And fairly soon, we should know the answer.
Whether or not the missing mass will be found in the infrared awaits further analysis. But past generations of stars did provide the IRAS survey with a major new finding. The discovery came directly from the images on their computer screens. It's called infrared cirrus, named after the wispy cloud in our atmosphere. Cirrus is interstellar dust, veil upon veil of it. It pervades the space between the stars, and IRAS saw it everywhere in our galaxy.
I personally find the cirrus fascinating from two different points of view. From one point of view, It's just the size of it. It goes throughout the entire galaxy. That means that it has structure which in many cases is on the size of 1,000 light years. It's really big, and there's some coherence to the whole thing, and that, I think, is an intrinsic interest in the cirrus itself. And that, by the way, I think is something that was really not expected. The second aspect which excites me about the cirrus is its effects on us looking outside of our galaxy, because the cirrus is blocking our view. And so that means that, in fact, our whole view of the outside world, we now know there's more obscuration than we thought there was initially.
The cirrus is so bright in the IRAS images because of its temperature. It's much hotter material than the astronomers expected to find. Perhaps one explanation is that the tiny dust grains of cirrus, only about the size of a molecule, can absorb starlight, but are too small to radiate energy themselves, and so store up heat. Astronomers do know that these clouds are composed of all the raw material for making the next generation of stars, and tell us that many have already passed. Until IRAS, the scientists hadn't seen the shadowy cirrus, not only because they lacked the tools, but because they didn't know what to look for.
It now turns out that if you look very well at optical photographs, carefully taken optical photographs, for example, one of the best telescopes is a survey telescope from the UK, which is in Australia. And if you inspect good photographs of that telescope, then you see weak emission on the sky. You see the optical picture, you see the plate has some emission everywhere, and that emission corresponds exactly to what we see in the infrared. But it's so faint that people haven't seen it, and on the older photographs you can't see it. It needs some expertise to make them. But it has been seen now, and the correspondence is beautiful.
But knowing what to look for, even with an instrument as sensitive as IRAS, did not always guarantee results, even when it looked closer to home. Little is known about the origin of our planets, except that they coalesced from dust particles and hydrogen and helium gas. There are 9 planets, including Earth. But astronomers feel there ought to be a 10th, because the orbit of Neptune wobbles in a way that suggests interaction with a body beyond Pluto, the outermost planet known.
The 10th planet has been both the bane and the boon of IRAS's existence. Ever since the beginning, people have realized that if there was a 10th planet, then it would be a very cool object, because it would be so far away from the sun that it can't be warmed up very much by the sun's radiation. Therefore, it would be most visible in the infrared and be very, very faint in the visual light. So IRAS's data will contain a 10th planet if such a one exists, because it's very sensitive to the infrared wavelengths. The problem has been is that everybody who's come to our facility, and everybody connected with the facility, has been on a mad search for the 10th planet, of course. And everybody who comes has done every search in every conceivable way of looking for an object, looking for objects that have moved over a period of 6 months, that have the expected temperature and so on, but no one has yet found out any evidence of a 10th planet in the data. So it's a very interesting search. It may well be there, but it's very difficult to say at the moment.
Originally, the astronomers had planned to set aside all the data from our solar system during the mission, because they doubted they'd see anything other than the man-made junkyard in orbit around us, or planets already well known. But one astronomer, Professor Jack Meadows, had other ideas.
The world, you might say, is divided, as far as astronomy is concerned, into the lords of creation who gaze at the universe and the grubbers after facts who look at the solar system. And most satellites are designed by the lords of creation, you understand. The original intention was to reject anything that moved. In other words, if it moved, don't shoot it. This seemed to me, I have a parsimonious soul, you understand, it seemed to me a pity. But I discussed with the British team members, who were extremely helpful, and then over with the Americans and the Dutch, the possibility of not rejecting this data, but of siphoning it off as it came in and examining it in real time. The team trying to pull out these data, went through just about the depths and the heights during the course of this, because it was not at all clear at the beginning we were going to detect anything. It was clear that the sensitivity was not what we'd expected, and therefore we didn't know whether we were going to pick up over a 9-month period anything at all, or just sit twiddling our fingers. So at the beginning, as a month passed and then another month, we had to spend most of the time banging each other's backs and saying, well, we're getting paid for it, and so forth. And then the first discovery, you see, and that first discovery was this incredibly bright comet that made the headlines and everything else. And suddenly you shot up to the peak and you were saying, we're in the middle of things, things are happening. It was really a remarkable oscillation.
They had sighted a previously unknown comet. It shed much more dust than comets had been thought to do, making it unexpectedly bright in the infrared. Named for the satellite and scientists that discovered it, IRAS Iraqi-Alcock burst its way into the news in 1983. Brighter than Halley's Comet, it passed within 3 million miles of Earth, the closest known approach of any comet within the last 200 years.
After that, every month except August, until the end of the satellite's lifetime, we picked up something of interest.
Within our solar system, IRAS went on to discover another 5 comets, each with a long, dusty tail. Our solar system is part of a larger galaxy. We see it at night as the faint serpentine band of stars called the Milky Way. It holds all the stars in our neighborhood of the universe. Here, IRAS turned up a revelation about the physical nature of the galaxy, a concentration of stars at the end of their lives.
One of the most striking differences in the optical results versus the IRAS results are that we can see much deeper into our own galaxy than optical results, visual results. In fact, if you look at this photograph, or this map of the stars, which have been picked out visually, this is looking along the edge of our galaxy, so looking into the galaxy. You can see that the stars that have been picked out visually actually seem to avoid the plane of the galaxy. The reason for these blank spaces in here is because optical light, visual light, doesn't travel very far through the galaxy. It gets scattered or absorbed, so that previous observers have only been able to identify these stars around the edge of the galaxy. With IRAS, we have this picture, a much different picture. You can see a heavy concentration of these sources to the plane of our galaxy, looking along the edge of the galaxy. You can see a concentration to the galactic bulge, which was only briefly hinted at in some of these studies. And the other thing is we have vastly more stars. We have more stars in our survey than all star catalogs have seen in the past. So we're going to gain a lot of information about these stars with the IRAS results.
Because IRAS could look so deeply into our galaxy, it was able to confirm its classic shape, something that had been suspected, but until the mission had never actually been seen. As the satellite swept across the sky, it investigated other galaxies, and it discovered many new ones, millions of light years beyond our own.
Before launch, we were hopeful of seeing perhaps 1,000 galaxies beyond our own Milky Way. The first source that we recognized for sure beyond the initial calibrator was in fact a galaxy. It was clear at that point we'd seen many, many galaxies, and indeed in the entire mission we've seen probably 20,000 galaxies or more.
The presence of these galaxies and the clues infrared can give about their behavior are critical pieces of evidence in the quest to understand the universe.
We discovered that there were galaxies which were far brighter at infrared wavelengths than we'd ever expected before launch, and far brighter than one would expect from their optical appearance in the sky. And one explanation of this is that these galaxies are undergoing vast quantities of star formation at very rapid rates. We don't really understand the reason for this. It may be that some of the galaxies are interacting with others, and it's this interaction which is triggering such events.
When one galaxy sweeps past another, their intense gravitational embrace stirs up the stars and gas in each of them. Their infrared activity suggests levels of star formation on a scale never before imagined.
These galaxies appear close together, and in many cases we think they actually are close together in space, as one galaxy goes past another, there is a tidal interaction, just as the moon causes tides on the Earth. And in some models of this interaction, at any rate, gas is stripped off one galaxy and plummets into the center of the other galaxy, and because it's moving at high speed and rushing into the center, it's in turmoil, and in the process creates a very large burst of star formation. It would be very nice to find out, in the case of many of the IRAS galaxies, just where this radiation, the intense infrared radiation, is coming from. Because if it is in the center, it would help to confirm some of these theories.
We'd always thought there would be galaxies with much starburst, what we call, going on. And so in a way that was expected, but it certainly wasn't predicted by analytic means. And the only way that you can find out about them is to just look at every spot and see what is it, really.
As the scientists ponder the secrets that IRAS has revealed, the closer they will be to understanding the origin and the fate of the universe itself. On November 23, 1983, the liquid helium keeping IRAS cool finally evaporated. The satellite quickly warmed up and the mission was over. Or was it?
We have thought up the instrument, we've designed and built the instrument, and we've made the observations. And now we're in the fun part. Now we're trying to understand what the observations are trying to tell us about our universe, about our solar system.
The analysis of IRAS continues today. Its huge catalog must contain many more exotic objects. For the scientists, the wealth of data collected allows them, in a sense, to fly the satellite over and over again. Just as the optical telescope revealed the visible universe to Galileo 3 centuries ago, IRAS has brought us the invisible universe. Stars and solar systems forming, new comets, cirrus, and starburst galaxies. Around the world, astronomers are swinging their great telescopes to look more closely at what IRAS found.
What we want to do now in the future is plan missions that let us zoom in and study in great detail what's going on within a particular galaxy, what's going on in a particular star-forming region. It's now the time for the very detailed studies of the objects that IRAS has revealed to us.
The next step beyond IRAS will be some sort of infrared observatory. And of course, the European Space Agency have already started to plan ISO, the Infrared Space Observatory. In this country, NASA is working on a somewhat similar concept of a space infrared telescope facility. We call it CERTIF. Using the same technology, improved detectors, which we're all working on these days, one would be able to fly a mission similar to IRAS, but with 1,000 times more sensitivity.
I think the important thing about IRAS is that since we didn't go with a preconceived idea, that what we are doing is seeing the entire universe. And I was reading in the paper today the comparison between the stars and grains of sand on a beach. And I think that we're now seeing all the grains of sand on the beach. And that's about how many we're seeing. I mean, we're seeing that same number. And now the exciting thing for us to do is to pick out which of the grains which are interesting and which tell us something about how the universe was formed. That's going to be the challenge now.
I kind of liken the excitement of the launch to perhaps the moment of Columbus setting forth to look at the New World. We knew that we were opening a new window on the universe and that this was likely to change man's entire outlook in ways that we could only guess at and conjecture about in some respects.
IRAS has uncovered the answers, or at least solved some questions and raised more questions about the nature of planet formation, about distant galaxies, distant quasars, the whole problem of star formation. All of these are questions that can only really be answered by studies at infrared wavelengths.
IRAS was a scientific and technological adventure of the highest order. It brought us a universe never before seen. images painted not with light, but with heat. In its 300 days in space, IRAS suddenly illuminated a new spectrum of the universe. And it seems likely that the biggest surprises and insights are yet to come.
For a transcript of this program, send $4 to NOVA, Box 322, Boston, Massachusetts, 02134. Please be sure to include the show title. Major funding for NOVA is provided by this station and other public television stations nationwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials. And the Johnson & Johnson family of companies, supplying health care products worldwide. The NOVA Space Explorer's Guide by Richard Moray is published by Clarkson Potter and is available in bookstores and libraries nationwide.